Hello, we are Group 19 and this is our project on exploring deep reinforcement learning algorithms in the car racing environment.
In the environment, the agent's goal is to navigate a track in the shortest time possible. We process the input of a 96 by 96 RGB image using a convolutional neural network to extract spatial features. The agent then outputs continuous actions for steering, gas, and braking. It is incentivized to make progress through a small positive reward for each newly visited track tile, kept efficient through a small per time step cost, and heavily penalized for leaving the track. Given the complexity of this task, where the agent must handle continuous control and complex box-2D physics like friction, tabular reinforcement learning methods are infeasible. Furthermore, because every track is randomly generated, the agent cannot rely on memorization, must instead learn a robust, generalizable driving policy.
We implemented several environment adjustments for our approach. Frame stacking enabled extracting temporal features like velocity and acceleration from the POMDP. And frame skipping extended the observation without increasing the input dimensions. For car control, the conflicting use of gas and brake and initial stochastic policy hindered movement. To address this, we reduced the speed controls into a single head, then mapped it to the action space. Repeating actions further reduced noise and reduced inference computation, while a minimum velocity constraint encouraged exploration. Unexpectedly, this also improved late training performance, with agents demonstrating better speed control. Lastly, we introduced early termination, which resulted in a more efficient and stable performance increase.
First method was PPO, a reinforcement learning algorithm known for stability and simplicity. Its clipped loss function prevents unstable policy updates. We implemented separate actor and critic heads. The critic estimates state value while actor outputs driving actions. Unlike standard implementations of PPO, which use Gaussian policies, we use beta distribution in ours. This is critical because cars controls are naturally bounded. So steering is between -1 to 1 and throttle is between 0 to 1, for example. Beta distribution respect these bounds by design, so we don't have to do any clipping, which causes gradient issues. We also added early stopping for poorly performing episodes to save training time, since off-track driving provides no useful.
We also implemented Soft Actor Critic, an off-policy algorithm specifically chosen for its superior stability in continuous control tasks. It's stronger than PPO in this environment for a number of reasons. First of all, instead of just maximizing the reward, we additionally maximize the entropy. This effectively gives the agent a curiosity bonus for keeping its options open and preventing collapse to safe behaviors like parking. And by using automatic entropy tuning, the agent drives aggressively at the start but more precisely later on. To prevent erratic steering, we introduce a second critic, where we take the minimum value estimate of the pair to prevent overconfidence. And finally, instead of throwing away data after each use, we use a replay buffer to store and relearn from past crashes, significantly improving sample efficiency.
We evaluated a simple vision-based baseline agent that drives forward and turns based on the colour of 2 pixels diagonally in front of the car, achieving a high mean reward. The SAC agent performed very well, with high mean and notably much lower standard deviation than the baseline, as it learned to correct itself when it made a mistake. In contrast, the PPO agent underperformed, with observations showing the agent failed to control steering and braking, often cutting or overshooting corners, and had very high standard deviation, as it did not learn to correct itself as well as SAC. Future work should explore transferability of our solution to more complex racing environments, such as multi-agent competition and 3D depth perception.